I want you, our listener, to just picture something for a second. Imagine you have this highly capable, incredibly smart AI assistant.
Right, like the ultimate productivity tool.
Exactly.
Yeah.
You totally trust it to manage your calendar, sift through your emails, maybe even handle your personal finances. It's seamlessly navigating the web on your behalf.
Doing all the heavy lifting.
Yeah. Now, imagine waking up one morning to find out that this brilliant assistant of yours just, wired a chunk of your money to a hacker.
Oh, wow. Yeah, that is the nightmare scenario.
Right. And it didn't happen because of some complex firewall breach or like a sophisticated phishing email that you clicked on.
No, of course not.
It happened simply because your AI assistant was asked to read a malicious product review on some random shopping website.
I mean, it sounds like a plot from a sci-fi thriller, right?
Yeah.
But it is an immediate, real-world vulnerability right now.
Wait, really? Just from reading a review?
Yeah. As we transition from these large language models that just sit in a chat window generating text to actual autonomous agents that take action in the real world, the security landscape completely changes.
Because they can actually do things now.
Exactly. The risks don't just add up, they multiply exponentially because the model is no longer just talking, it is doing.
Man, that's a lot to take in. And to help us unpack this today, I'm joined by our resident expert on AI architecture, sitting right here as the second mind in the room, with you, our listener, as the crucial third.
Glad to be here for this.
Okay, let's unpack this. Our mission today for this deep dive is to break down a state-of-the-art research paper. It's titled AgentSys Secure and Dynamic LLM Agents Through Explicit Hierarchical Memory Management.
It is quite a mouthful.
It really is. But, what makes this paper stand out isn't just that it identifies the problem, it proposes a really brilliant architectural fix that completely flips how we think about agent memory.
Right, aiming to secure these systems without, crippling their actual usefulness.
Yeah, exactly.
The structural approach they take here is what makes this a true paradigm shift.
Mm-hmm.
But, well, before we get into the solution, we really have to look under the hood at how these agents currently operate.
Makes sense. Got to understand the problem first.
Right. Because the way a standard AI agent manages its memory is precisely what makes it so uniquely vulnerable to these very specific kinds of attacks.
Yeah. Reading through the sources, the best way I can describe a current LLM agent is that it's basically a digital hoarder.
That is a very accurate way to put it.
Right. It's like someone who just refuses to throw away a single piece of paper that crosses their desk. When you give an agent a task, it uses what's called a context window as its working memory.
It's short-term brain, essentially.
Yeah, exactly. And the standard design right now is that every single thing it encounters just gets permanently piled onto the desk. Every tool output, every intermediate reasoning thought, the raw HTML of a web page it visited.
The entire history of your conversation.
Yes. All of it. It just accumulates. So eventually, this hoarder gets completely confused because a scam flyer is sitting right next to their actual electric bill.
Right. And that hoarding behavior doesn't just stop at confusion. It actively opens the door for what security researchers call indirect prompt injection.
Indirect prompt injection.
Okay, yeah, or IPI. Because the agent pulls in this unverified external data and treats it with the exact same weight as the user's core instructions.
Wow. So it can't tell the difference between me telling it to do something and a random website telling it to do something.
Exactly. An attacker simply has to hide a malicious command somewhere the agent is, likely to look. They embed it in a web page, a document, an email inbox.
Like my opening example, a product review on Amazon.
Precisely.
That is so wild. The user is completely innocent here. They just ask the agent to go fetch the web page or summarize the reviews.
But the agent drags that hidden malicious command right back into its own central memory.
So what does this all mean? If a user just asks an agent to fetch data, are they essentially pulling the trigger on their own hack?
Unfortunately, yes. What's fascinating here is that the AI is doing exactly what it was programmed to do. It reads, it remembers, and it follows instructions.
It's being a good assistant.
Exactly. The vulnerability is structural. The agent's inability to forget is the actual weapon here. And the researchers highlight two massive problems caused by this full memory accumulation.
Okay, let's hear them.
The first is attack persistence.
Right, because it never throws the bad instruction away.
Right. Once it's on the desk, it stays on the desk. Because the memory is cumulative, if an injected instruction enters the context window during, say, step 1 of a multi-step task, it stays there for step 2.
In step 3 and step 4.
Exactly. The agent is forced to reevaluate that malicious code every single time it makes a subsequent decision.
Oh, that's terrible.
The attacker essentially gets multiple bites at the apple. They're constantly whispering in the agent's ear, and the study's data illustrates just how dangerous this is.
Yeah, what did the numbers look like?
If an attacker manages to inject a prompt in the very first round of a 4-step task, they have an attack success rate of over 60.5%.
Wow, over 60%.
Yeah. But if that injection doesn't happen until the third round, the success rate drops to just 5.88%.
That is a massive drop.
It is. The longer that instruction sits in memory, the more it contaminates the entire reasoning process.
So an early infection basically just rots the whole workflow from the inside out.
Absolutely.
But looking at the paper, there's a second major problem with this hoarding behavior, and it actually has nothing to do with hackers at all. It's utility degradation.
Yes. The sheer bloat of information.
Right. Even in a perfectly safe environment with zero malicious instructions, a bloated memory literally makes the AI less capable.
Because the AI's attention mechanism gets completely diluted. Think about how transformer models work, right? They have to calculate the relevance of every single token against every other token.
Which is a huge mathematical operation.
Huge. And when you dump raw tool outputs into the context window, you're including massive amounts of metadata, formatting code, verbose junk that the AI just doesn't actually need.
All the HTML tags and stuff?
Exactly.
Yeah.
And the study found that standard, undefended agents perform decently on short tasks. They complete them with around a 44.6% success rate.
Okay, almost 45%. Not great, but okay.
Right. But on long tasks, where that memory window really starts to bloat with all that accumulated junk, their utility drops to a dismal 19.08%.
19%.
Yeah, they just lose the plot completely. They get buried under their own paperwork.
That is a staggering drop in baseline performance. I mean, we have a system that is both highly vulnerable to attack and fundamentally inefficient as tasks get longer.
It's the worst of both worlds.
So if hoarding is the disease, what have we been using as the cure up until now? Because engineers have obviously seen this problem coming, right?
They absolutely have. And the paper categorizes existing defenses into 3 distinct layers.
Okay, let's go through them.
The first layer is model-level robustness. This relies on prompting strategies, things like prompt sandwiching or spotlighting.
Right, I've seen this. The idea is to bracket the external data with strong reminders of the original task. So you put the user's instruction at the top, drop the messy external web page in the middle, and then put another reminder at the bottom.
Exactly. You literally make a sandwich out of it.
But, I mean, the glaring flaw there is that the bloated memory is still fully accepted. The malicious instruction is still sitting right there on the desk. You're just hoping the AI has the willpower to ignore the bad instruction in the middle.
Relying on its focus, yeah.
But against a sophisticated injection that specifically tells the AI to, ignore the sandwich, that seems incredibly fragile.
It is incredibly fragile, which leads to the second layer, detection-based guardrails.
Okay, how do those work?
Well, systems like Protect AI or PyGuard try to build a firewall. They use separate classifiers to aggressively scan the incoming text and filter out anything that looks like an injected command.
Before it ever reaches the agent's memory.
Right.
Wait, if we have these smart LLMs, why can't we just build an incredibly aggressive filter to sanitize every single thing the agent reads before it enters the brain?
Because if you aggressively filter the incoming information, you inevitably run into false positives.
Ah, you filter out the good stuff by accident.
Exactly. You strip out the benign context the agent actually needs to do its job. It's the classic trade-off between security and utility.
It's like trying to secure a library by burning all the books.
That's a great way to put it. You solve the security problem, but you don't have a functional library anymore.
Right.
And looking at the data, using that aggressive filtering with Protect AI drops the agent's benign utility down to around 40.64%.
So you're making the agent safer, but vastly less useful.
Precisely. Which brings us to the third attempt, which is system-level control.
System-level control, like what?
Frameworks like ISIL-EDPT or CAML, they take an architectural approach. They put the agent in a very rigid sandbox, strictly defining exactly what tools it can call in what specific order.
Very constrained data flows.
Right. And from a pure security standpoint, it works. CAML, for instance, drops the attack success rate to a literal 0%.
0%. Okay, but wait. If you're restricting the AI's environment that severely, you must be crippling its ability to reason dynamically.
You're absolutely right.
I mean, the whole point of an autonomous agent is that it can creatively solve open-ended problems, right? It adapts to new information, figures out multi-step solutions on the fly.
Right, that's the drawer.
If you put it on rigid, predefined tracks, it's just a traditional software script again. I'd imagine the utility plummets, just like it did with the filtering method.
Oh, it plummets even further. With the Camel sandbox, that benign utility crashes down to roughly 29.97%.
Less than 30% utility.
Yeah. So to summarize the current landscape, if we let the agent keep its hoarder habits, it gets hacked and gets confused.
No.
If we prompt it to ignore bad inputs, it gets tricked. If we aggressively filter, we strip its context. And if we lock it in a rigid sandbox, we strip away its intelligence entirely.
Wow. It just feels like a complete no-win scenario, which is why this AgentSys framework feels like such a massive breakthrough.
It really is.
The researchers just stopped trying to patch a flawed, bloated memory system and instead asked, what if we restructure how memory works from the ground up?
They looked outside of machine learning entirely.
Yeah, they took inspiration from how traditional computer operating systems isolate process memory. And to visualize this, let's use a CEO and interns analogy.
I like this one. Walk us through how that maps to the architecture.
Okay, so in the AgentSys framework, the system is split. You have the main agent acting as the CEO.
Okay.
The CEO holds the global context, the big picture of what the user actually wants, the overarching plan, the final goal.
The executive vision.
Exactly. Then you have the worker agents, which are like short-lived, highly focused interns dealing with the local context.
The specific tasks.
Right. Now, imagine the CEO needs a new client's email address from a massive, completely disorganized filing room. The filing room being the external internet or a messy inbox.
Sure.
In the old hoarder system, the CEO would just walk into the filing room, pull every single file, dump them all on their own desk, and try to sort through the mess.
And that is exactly how the malicious junk mail ends up permanently in the CEO's brain.
Exactly. But with AgentSys, the workflow fundamentally shifts. The CEO refuses to go to the filing room.
Smart CEO.
Right. Instead, the CEO writes down exactly what they need on a highly specific request form. The paper calls this the intent schema, which demands a strict JSON data structure.
JSON, yeah. It's very rigid.
Yes. The CEO dictates, I only want a document that contains an email string, nothing else. Something like open bracket, quote, email quote, colon, quote, string quote, close bracket.
Very precise.
They hand this schema to a newly spawned worker agent, the intern. The intern goes down to the chaotic filing room, fetches the raw, messy tool output, and performs the extraction.
And the crucial boundary here is that the raw tool output only ever goes to the intern. It never touches the CEO's desk.
Never. The intern sifts through the raw data, finds the email address, formats it into that exact JSON structure, and hands only that clean, structured data back up to the CEO.
And then the intern is dismissed. The worker agent is totally ephemeral.
Gone.
If we connect this to the bigger picture, this structural separation is profound because it addresses both of our major problems simultaneously.
Right, because the CEO's desk stays clean.
Exactly. The CEO never sees the verbose metadata, the HTML formatting, or, most importantly, the hidden prompt injection telling them to wire money to a hacker.
Wow.
The CEO's desk stays perfectly clean, which inherently prevents the utility degradation caused by attention dilution. And because the malicious prompt never enters the main memory, it completely stops attack persistence.
The malicious instruction just dies with the intern.
Yes.
The elegance of it is so striking. I mean, the paper actually ran an ablation study where they turned off all other complex defenses and just tested this one mechanism.
Just the isolation.
Yeah, just the context isolation of the CEO and intern structure. And the attack success rate plummeted to roughly 2.19%.
That's incredible.
Just by changing who reads the mail and enforcing a strict communication boundary.
It really proves that principled memory management is the absolute foundation of security. You don't need 1,000 complex AI-driven filters if you just enforce a rigorous structural boundary between the planner and the executioner.
Okay, so the CEO is safe, the big boss is protected, but what happens if the intern, the one actually handling the poison data in that chaotic filing room, what if they go rogue?
Right, because they are still exposed to it.
Yeah, we can't just let them run amok with the company credit card. If the intern reads a malicious product review and gets compromised during their local task, we need safety nets for those subtasks.
We do, and that is where mediated recursion comes into play.
Mediated recursion, okay.
Sometimes the intern needs to use a tool to get the information. And maybe they need to use another tool based on what they find. They might need to execute a multi-step search locally.
Right.
To manage this, the researchers built in a strict oversight mechanism called the validator. If a worker agent needs to use a tool to fetch more data, an LLM-based alignment checker steps in as a gatekeeper.
Okay, so it verifies that the intern's planned action actually aligns with the CEO's original intent schema.
Exactly. It checks their work before they actually push the button.
But there has to be a catch, right?
Well, there's a vital optimization here that makes the system practical in the real world. The validator only checks command tools.
Command tools? Like what?
These are actions that have external irreversible side effects, like sending money, deleting a file, sending an email.
Things you can't undo.
Right. It ignores query tools, which are just read-only actions like searching a database or reading a web page. This keeps the system overhead incredibly low.
Okay, but here's where it gets really interesting, but also maybe a bit concerning from an engineering standpoint.
Go on.
If we are constantly spawning all these ephemeral interns, and we have a separate LLM validator checking their work every time they try to execute a command, and then we have to deal with them if they make a mistake.
The compute cost.
Yes. Isn't this system going to be impossibly slow and expensive to run? You're trading a security problem for a massive compute problem. Isn't the token cost going to be astronomical?
It's the necessary question for any real-world deployment, absolutely. Every time an LLM processes text, it burns tokens, which translates directly to compute cost and latency.
Right. So what are the numbers?
The researchers did a deep dive into this token economy. An undefended baseline agent uses about 0.82 million tokens.
Okay, under $1 million. Pretty cheap.
It's cheap, but as we know, it's highly vulnerable. AgentSys, on the other hand, used about 3.25 million tokens.
Oh, wow. So it is a lot more.
So yes, it is more computationally expensive than doing nothing.
It's roughly 4 times the cost. That is a significant overhead for developers to consider.
It is a cost increase, but let's evaluate it against the alternatives that actually provide tangible security. Remember the CAML framework? That rigid sandbox?
Yeah, the one that dropped utility to under 30%?
Exactly.
Yeah.
Well, CAML uses over 6 million tokens.
Wait, really? 6 million?
Yes. It costs almost double what AgentSys costs, and it completely breaks the agent's utility. To capture the full picture here, the researchers created what they call a defense quality metric.
How does that work?
It multiplies benign utility by security. The baseline score is around 44. CAML, despite its massive token cost, scores an abysmal 30-point-something because it renders the agent largely useless.
Right, makes sense.
AgentSys achieves the highest defense quality metric of 63.86. It is the optimal sweet spot. The cost scales only with actual command operations, not by forcing a massive model to constantly reread a bloated history on every single term.
Okay, that makes total sense mathematically. Because the CEO's memory is kept incredibly short and dense, you aren't paying the token cost to reread the junk mail on every single step of a long task.
Precisely.
Okay, but I want to dig into the mechanics of a failure. Let's say the intern reads the malicious prompt and gets hijacked.
Right.
They try to execute a command to send money to the hacker. The validator steps in, sees the misalignment, and says, deny.
Yep.
Does the whole system just crash and throw a fatal error to the user?
It doesn't crash, no. And this introduces the concept of bounded recovery, or the sanitize-restart loop.
Sanitize-restart.
Right. If the validator denies a command, the system assumes the external tool output the intern just read was poisoned. It triggers a sanitizer.
Does it just delete the whole file?
No. Rather than aggressively filtering everything, the sanitizer specifically scrubs instruction-like text from that specific piece of data.
Oh, interesting.
It replaces the malicious string with a safe placeholder while maintaining the data structure. Then it tells the intern to try again with the sanitized data.
It essentially says, go back to the filing room, look at this file again, but we've blacked out the mind control rays. Try to extract the email address now.
The mind control rates, exactly. But the key here is that this loop is bounded. There is a strict retry budget to prevent the agent from getting stuck in an infinite loop of failing and retrying.
Because that would just burn through tokens forever.
Right. If it fails a set number of times, it explicitly reports a failure back to the CEO. It basically says, I couldn't safely extract the email address.
Gotcha.
The CEO can then decide how to proceed with their overarching plan, without having their own central memory contaminated by the failure.
The CEO never gets infected. They just get a clean, actionable error report. They can pivot and try a different strategy.
Exactly.
All right, so we've mapped the theory, we've explored the architecture, the mechanics. Let's look at how this actually performed in the real world when stress tested against adaptive attackers.
This is where it gets really exciting. The benchmark results are genuinely remarkable. They ran AgentSys through the AgentDojo benchmark, which is a standard gauntlet for testing agent security in simulated environments.
Like booking flights or managing inboxes, right?
Exactly. And they used GPT-4o Mini as the underlying model. The attack success rate dropped to just 0.78%.
Under 1%.
Yeah. And on another rigorous benchmark, ASB, it dropped to just 4.25%.
Those are massive security gains. But, I mean, my immediate assumption is that by restricting the AI's memory and forcing it through this rigid CEO and intern pipeline, the utility must have taken a hit. Maybe not as bad as the sandbox, but surely it lost some reasoning capability.
You'd think so, right? But the benign utility actually improved.
Wait, improved?
Yes. The undefended baseline had a 63.54% utility score. AgentSys achieved 64.36%.
Okay, let's unpack this. By enforcing amnesia on the main agent, by explicitly taking information away from it, it actually became more capable. It got smarter.
It really did. This raises an important question about how the entire industry views AI context.
Yeah, how so?
Well, for years, the prevailing assumption has been that more context is inherently better. Build larger context windows, feed the model absolutely everything, give it maximum situational awareness.
Right, everyone brags about their million-token context windows.
Exactly. But this paper proves that curated context is infinitely superior to infinite context.
That is a profound shift in design philosophy.
You can see the mechanics of this clearest when you look at the trajectory length data. Trajectory length simply refers to how many tool calls a specific task requires.
Okay.
For short tasks, the baseline models do fine. But for long tasks, tasks requiring more than 3 tool calls, the baseline utility of normal agents crashes down to 19%. They literally get lost in their own accumulated memory.
Right, the hoarder problem we talked about.
Yes. But AgentSys remains incredibly strong, maintaining 24.58% utility on those highly complex multi-step tasks.
Because the CEO's desk is still clean on step 5 or step 10, they haven't lost sight of the primary goal because they aren't bogged down by the formatting metadata from step 2.
That's it, exactly. And the security holds up even better over time as a direct result of this cleanliness. For trajectories of 4 or more tool calls, the AgentSys attack success rate drops to a literal 0%.
Wow.
The isolation boundary prevents any initial contamination from rolling forward and biasing downstream decisions.
Yeah.
It simply starves the attack of the persistence it needs to survive a long task.
I want to dig into one specific stress test from the data before we wrap up, because I know anyone with a cybersecurity background listening right now is thinking, what if the hackers know exactly how AgentSys works? What if they specifically design an attack to sneak through that JSON intent schema?
It's a very valid concern. The researchers actually anticipated that exact scenario and tested it using the PAIR attack.
PAIR attack, what does that stand for?
Prompt Automatic Iterative Refinement. Instead of a human writing a static malicious prompt, you use an attacker AI to constantly rewrite and refine the prompt.
Oh, wow. So AI versus AI.
Exactly. It plays a game of chess against the defender, it tweaks its phrasing, watches how the system fails, and rewrites it to find a way past the defenses. It is an incredibly aggressive, adaptive red teaming approach.
So the attacker AI knows it has to get a malicious payload onto the CEO's desk, and it knows the only way up is through that JSON intent schema.
Exactly. And even when an adaptive AI specifically tries to format its malicious code to perfectly camouflage inside a benign string field within that strict JSON schema, the system held up.
Really? How well?
The attack success rate only rose slightly to around 2.06%.
Just 2% against an adaptive AI attacker. That's wild.
It remains robust because even if a bad string manages to sneak past the intern and onto the CEO's desk, the structural boundary prevents it from executing. The CEO expects a data string, not a command. It prevents the payload from hijacking the main agent's overarching logic flow.
It is a masterclass in defensive engineering. I mean, to quickly recap the journey we've been on today, we started by looking at how the default design of LLM agents turns them into digital hoarders.
Right.
By accumulating every piece of data in a massive context window, they become highly vulnerable to indirect prompt injections, and their reasoning degrades over long tasks. We saw how existing defenses either failed to clear the memory, or they locked the AI in a sandbox that made it effectively useless.
And AgentSys solved this by pulling a foundational concept from operating system design.
The CEO and the intern.
Exactly. By creating a hierarchy, a main agent managing global context and worker agents handling local tool execution, and enforcing a strict JSON communication contract between them, they prove that you can keep the agent's central memory completely secure.
And in doing so, they solve the utility problem, too.
Right. They prove that a clean, curated memory enables an AI to reason far better on long, complex tasks.
You know, it is the difference between having a helpful, brilliant assistant who manages your life seamlessly and waking up to find a catastrophic security breach because your AI read the wrong review on Amazon.
It really puts it into perspective.
As you, our listener, begin trusting AI agents to autonomously book your flights, read your personal emails, and execute real-world tasks, this memory architecture isn't just an obscure engineering problem. It is the foundational blueprint for a future where we can actually trust these systems to act on our behalf.
It really is the architecture of trust.
I want to leave you with a final thought to mull over today. We spend so much time marveling at how much these large language models can remember and how vast their context windows are becoming with every new release. But if giving an AI a massive, unlimited memory makes it inherently more vulnerable to manipulation and distraction, does true digital intelligence require the ability to actively forget?
A fascinating question to end on.
Thank you so much for joining us for this deep dive into the foundations of generative AI. We invite you to keep questioning the architecture of the tools you use every day. Until next time.